Hi folks, we're taking a look at GDC techniques for paper 2 for your IB Math Standard Level exam. This presentation will show you pretty much everything you'd need to get by, but in a lot of cases there's another way to find it on your calculator. I should mention that this is geared towards the TI-84 calculator, and also it's with the new operating system, OS 2.55. And if you don't have it, it's probably worth getting for your calculator because it makes a few things a little bit easier. Alright, you have to be able to do some basic things with the function menu. So you need to be able to use the calc menu on your calculator. Let's suppose we wanted to use this function here. F of x is 2x squared minus 12x plus 13. All I'd have to do is put it into my calculator, which of course you know by now. I've got it in there for y1. And if I wanted to find, say, f at 2, rather than doing it by hand, which really wouldn't be very much work at all, I can always go to the graph. Okay, there it is. It's a parabola. We're not surprised. I also have another graph G on there. But I can go and find the value for f at 2. So I just go second calc 1. I want the x value of 2. And it tells me, it gives me a y value of negative 3. So that's pretty slick. 0 calculates the x values where f of x is 0. In other words, it finds the x-intercepts. So if I wanted to find the x-intercept of that graph, first of all, I'm going to turn off my linear graph. If I want to find that first x-intercept, what I'll do is second calc, find the 0. I have to go to the left of it. So you can see here that I'm a little to the left of my x-intercept. I press enter. I need to go to the right, a little to the right. And I guess, I just go right next to that x-intercept. It tells me it happens at 1.42. Okay, and there's also going to be another one as well. And we just go through the same process to find it. Max and min, pretty straightforward. Finds the maximum or minimum over a certain interval. So on this parabola, obviously there's no max. There is a min, though. So we'll go second calc, choose 3 for a minimum. And again, it asks us for left bounds and right bounds. So we need to go to the left of the minimum, press enter, go to the right of the minimum, press enter, guess. And there, we get a minimum of negative 5 at an x value of 3. Whoops. So we found out that f at 3 is negative 5. In other words, the min is negative 5. On a paper 2, you don't want to waste your time doing any functions by hand that your GDC could do quickly. So if you needed to find a min, that's probably the way to go. Okay, intersect finds the point of intersection between two curves. So I had that f of x and g of x function from the last page. One was a parabola, this one right here, and one was a line. We can find out where those two intersect. So I'll turn on the linear function again. Two graphs, there they are. To find the point of intersection, I just go second calc, 5 for intersect. It asks me, is this the first curve where it says y1? Yep. I want the quadratic one to be one of my curves. y2, I want that to be the second curve. And it also asked me to guess. And I need to do a half-decent job guessing here. And it looks like there's a point of intersection at 1.11 and 2.11. Or 1.11, 2.11 as the coordinates. And there's another point of intersection a little further along. So I just go through the same process again. Okay. Second calc, 5 for my intersection. First curve, yep. Second curve, yes. And now I need to go and guess closer to that second intersection, which occurs at 5.39, 6.39. This intersect function is probably one of the most powerful ideas for your paper 2. Whenever you have an equation to solve, you can always solve it graphically. So if we look at right here, we have 3e to the x equals 2x plus 6. That's going to be a miserable equation to solve analytically. But if we go to our calculator, all I need to do is put in for y1 one side of that equation. So I'll turn off my other functions. On the left-hand side, I have 3e to the power of x. On the right-hand side, I have 2x plus 6. I graph those, and I look for any points of intersection. Now I still have to know something about the look of the graph 3e to the x. I need to know that there's going to be an intersection here and an intersection up here. I don't know why it puts the little circle with the line through it there, but there is one there and there is one down here. So I'll go through that process again, find the point of intersection. First curve, yeah, y3 is my first curve, y4 is my second curve, and I need to guess somewhere around -3-ish. So there's an intersection at -2.92. Notice that in the original equation, there are only x's. There's no point in putting the y-coordinate of the intersection in. So to solve this, we're going to happen to have a solution at -2.92. And also another intersection. First curve, second curve, yep. At around 1-ish, it looks like. 0.974. To use a graphical solution, you needed some decent window settings, but it saves you a lot of time when you have tricky equations. Alright, in your calc menu there's also this dy by dx, which means the derivative, and it's the derivative at a certain value. So we've got, let's go back to our parabola that we'd been working with. I'll turn on that graph and turn off the others. If I'm asked to find f prime at 2, it's asking me for the slope or gradient at 2. All I need to do is graph it. It looks like at 2, I'm going to have a negative slope, somewhat steep. I just go second calc, 6 for the derivative, and tell it I want to use an x value of 2. So I'll just go through that again. Second calc, 6, an x value of 2, and it tells me that the slope or gradient there is -4. Again, pretty slick. It wouldn't have been hard to differentiate the function of f, but this saves us a tiny bit of time. Similarly, if I wanted the integral from 1 to 5, that might be hard to read, I can use second calc 7. So this all does it on the graph. Again, I'm using my quadratic. I'm going to go second calc 7. I want a lower limit of 1 in this case, and an upper limit of 5. I find that the integral over that range, or between those boundaries, is -9.33. Okay? Which isn't exactly the same as the area bounded by the curve and the x-axis. But it does have applications in area. I want to draw your attention to a few of the features that are in the new operating system that are kind of nice. And a lot of these features you can find under alpha y equals. Okay, so if I press alpha y equals, I get, first of all, 4 separate menus. One says frac, which is for fractions. Then there's func for different functions, matrix, and then your y variables. Okay. So under the frac, there's a nice way to put in fractions. This first one, n over d, just means numerator over denominator. So if I'm given this function over here, h of x is 3x minus 2 over x plus 1, I might forget to put in some brackets without having it in actual fractional form. This way I can go y equals, I'll quit here. I'm going to put in a new function, so I'll call this my y5. Alpha y equals gets me to this menu. Yes, I want numerator over denominator. And now it makes a nice fraction that we can work with. So I can put 3x minus 2 on the top and x plus 1 on the bottom. You could obviously do this before. It's just that you had to remember some brackets. And it's nice and easy to find now. Okay, the sigma is pretty nice as well. I don't think you should really need it, but nice to have there. So if I want to evaluate the sum of the first 20 terms, where we have each term defined by 2p minus 3. Obviously, you can write the first few out, realize what kind of sequence it is, find the sum of the corresponding series. But the other thing you can do is just, we'll quit and go to a blank screen. I go alpha y equals, go to func, and go down to 2. There's my sigma. And I'm going to have to tell it exactly what to evaluate. So I want to go from x equals 1 all the way to 20. I'll use x instead of p. Of 2x minus 3. And it just works it out for me. Now, a word of caution here. This doesn't absolve you of the responsibility of knowing what sigma means. But on a paper 2, it might save you a tiny bit of time. Okay, so we're able to do that pretty quickly. N deriv. So this finds the derivative at a specific point. I don't really like this. I prefer to do it on the graph. So we did this under Second Calc 6 on the last slide, where we found, we're looking here for, this should say f prime at 2. So how we did it before was, we went to the graph, and we just went Second Calc 6, and asked it to find the derivative at 2. The other way you can do it is under this alpha y equals, go to the func, n deriv. So you want the derivative with respect to x of 2x squared minus 12x. I have to make sure I come down. Minus 12x plus 13, where x is 2. And it gives me the same thing, that it's negative 4. I really like having the visual confirmation for the derivatives. The integrals, though, are really nice. So in this next one, we're going to find the integral from 0 to 3 of x plus 1 dx. I'll go to my alpha y equals again, go to the functions, go to the fn int. And the notation is so nice here. You get to put it in just how you see it. So from 0 to 3 of x plus 1. And it reminds you that you need to tell it what you're integrating with respect to. So dx, lovely, gives us 7.5. Alright, the last thing that's in there that might be useful to you is log base. So typically your calculator is only working in a log with a base of either e or 10. This allows you to work in any base. But you can already do that from your change of base rule. So again, I'd go alpha y equals, go over to func. It says log base. I get to tell it that I want log base 2 of 7. Okay. Tells me that's about 2.81. Which makes sense. 2.81 rather. But you could have also done it with pretty straightforward ln 7 over ln 2, or log base 10 over or of 7 over log base 10 of 2, or log of any base of 7 over log of that same base of 2. Okay. So I don't really think you need the log base, but it's kind of cute to have it. Okay, matrices, we're not going to go through a whole lot in terms of matrices. It's pretty straightforward. Second, x to the negative 1. You need to be able to input matrices of any order and perform operations. Raise a square matrix to an exponent, find the determinant of a square matrix, find the inverse. Okay, so let's just go and quickly take a look in the calculator what that looks like. I go second, x to the negative 1. First thing I'd need to do is create a matrix. So say I wanted a 2 by 3 matrix. There we go. There's a 2 by 3 matrix. 1, 3, 5. Let's say it has a 0, negative 2, and a 6. There we go. I can go and do stuff with that matrix. I could multiply it by another matrix I'm about to make. There's some things that it'll let you do, so you can find the determinant, but we can't find the determinant of the matrix we just made because it's not square. So let's do another matrix. We'll create a 2 by 2 matrix. Let's say it's 1, 5, 3, and 6. If we wanted to get the calculator to find the determinant, we just go over to, we want the determinant of matrix B. And it tells us that its determinant is negative 9, which in turn tells us that this matrix is invertible. Okay. You can find the inverse just by going B to the negative 1. Okay. And it gives you, in decimal form, the inverse of the matrix. Some things to remember. Dimensions of a matrix are given by number of rows, by number of columns. You get to confirm whatever you put in your GDC because it actually shows you. So if you say it's a 2 by 3 matrix, it'll show you that you have 2 rows and 3 columns and what that looks like. Remember that order matters when multiplying matrices. That you can't divide matrices. And a matrix has an inverse only if it is square and its determinant is not 0. On the point that order matters, the point that order matters when we're multiplying matrices, I've just got a few little examples here. If AX equals B, then to get rid of this A at the front, we need to put an A inverse right beside it. So that's A, looks like A negative 1. Since I multiplied in front on the left side, I need to do the same on the other side. And these two things will just give us the identity matrix, so essentially we'll be left with X on this side. And on the other side, we'd have A inverse times B, assuming that that's possible. So the A and the A inverse need to go right next to each other. Let's take a look at the next one. It's subtly different. XA equals B. So to get rid of that A, I need to put an A inverse right beside it, which means it's coming at the end of the side. I'm post-multiplying. So as long as I do the same thing to both sides, and order matters, what I'll get is X is B times the inverse of A. Okay, so see how those two are different. Order matters. On the next one, A inverse times X equals B. I need to pre-multiply both sides by A, so I get X equals AB. And the last one, X times the inverse of A. I need to post-multiply both sides by A, and I get X as BA. So just be careful about the order. Okay, basic statistics. You need to be able to use your GDC to quickly find mean, median, standard deviation, and quartiles. There are two possible scenarios. So in one of them, you're given some raw data, just a bunch of numbers. So let's suppose we're given the numbers 5, 7, 8, 10, and 3. We're going to press the Stat button and access our lists. So let's do that. Stat, go into your lists. We're going to enter our data in list 1. So our data was 5, 7, 8, 10, and there was also a 3. Okay. And then I'm going to quit. We're going to choose one variable stat, so that's stat and then over 1. Stat, go to calc, one variable statistics, always one variable statistics. Press L1, so our list that we're using, that we put all our information in, was L1. We have no frequency list because this is raw data. So L1 to tell our calculator where to find the data, and leave the frequency list blank if it's just raw data. And then it'll go and calculate. So it tells us all this great stuff, that the mean is 6.6, that the standard deviation is 2.41, that there are 5 pieces of data, that the sum of all the data is 33, that the min is 3, we knew that, first quartile would be 4, the median 7, third quartile is 9, and the max is 10. You could also be given a frequency table or graph. So here's a little frequency table. We've got 3 different scores, 0, 1, or 2. And 12 people scored 0, 39 people scored 1, and 6 people scored 2. We're going to enter our data values, which would be just the 0, 1, and 2 in list 1. And that means clearing out what's already in list 1. So let's go in list 1. I go up to the heading and press clear, enter. All gone. 0, 1, and 2 are the different actual scores. And in list 2, I'll put in my frequencies. Now, just a quick word here. If instead of having numbers here, you had had class intervals, so say it had been from 0 to 10, all you would do is put in for your score the midpoint of those intervals. So you can't put in an interval in your list in the calculator. You'd have to use the midpoint. Okay, now we've got our frequencies in list 2. I'm going to quit, second mode. I'm going to go again to one variable statistics and tell it that we've got our values in list 1. And in list 2, that's where we have our frequencies. And now it'll go ahead and calculate. It gives us a mean of 0.895. Standard deviation of 0.552, etc. It gives us all the relevant information. Alright, features involving the normal distribution. So these features are found under the distribution menu, which is second vars. The features that we use are normal CDF and inverse norm. You could also use shade norm instead of normal CDF. It's kind of nice. Then you get some visual confirmation of what you're doing. If a question involves z-scores, we should know that that means we have a mean of 0 and a standard deviation of 1. So if we wanted the area between some given z-scores, it's the normal CDF function that does that for us. One of my markers is freaking out on me. Normal CDF. Okay, I'm just going to move this over. So if I want the area that is between negative 0.45 and 1.03, and we're talking about z-scores, then that must be on the standard normal curve, which has a mean of 0, this area between 1.03 and negative 0.45. I might shade it in. To find that area using my calculator, here's what I do. I go second vars, normal CDF, or you could go over to draw and use shade norm. The lower boundary is negative 0.45. The upper boundary is 1.03. In this case, we have a mean of 0 because it's the standard normal curve. So the z-scores tell us that it's going to be mean of 0 and standard deviation of 1. Paste. Yep. Evaluate. Tells us that that area is 0.522. Okay, pretty straightforward. Area to the left of a given z-score. So in this case, we're looking at probability that z is less than negative 0.34. I'm going to draw it. I always draw these ones. I think that's a great plan. That way, you know roughly what's a reasonable answer. So to the left of negative 0.34, I know I should get an answer that's less than 0.5, because less than half the curve is shaded here. All right, your calculator doesn't understand this notation of just less than negative 0.34. So how we think of it, instead of saying probability of z being less than or equal to negative 0.34, it's the same as z is between negative 0.34 on the upper side and a lower boundary of negative infinity. Now your calculator doesn't have a negative infinity button, but you can choose a very large negative number. And it actually doesn't matter really how big you choose, as long as it's at least 100. It's not going to make a difference. So let's go back to the calculator. If we wanted to do this one, probability that z is less than negative 0.34, we'll go to the distribution, normal CDF. I'm going to tell it my lower boundary is negative infinity, which I'm going to approximate with negative 10,000. Okay? Because it's not going to make a difference. When we talk about negative 10,000 standard deviations away from the mean, that's pretty remote probability. All right, the upper boundary is negative 0.34. The mean is 0, and the standard deviation is 1 because we're talking about a z-score, or a standard normal curve. Gives us 0.367, which is a reasonable answer, less than half the curve. Similarly, area to the right of a given z-score, if we want to find the area to a z-score of negative 0.56, we'd write this in this way. But the calculator wants it interpreted as between negative 0.56 and, you guessed it, positive infinity. Okay, we don't have a positive infinity button. We just pick a high upper boundary. So probability that z is greater than or equal to negative 0.56. Again, I'm going to sketch it. Negative 0.56 is somewhere over here. Yeah, that should be an answer that's greater than 0.5. It's more than half the curve. Second vars, normal CDF. Our lower boundary now is negative 0.56. Our upper boundary is positive infinity, which I'm going to approximate with something pretty big. Again, mean 0, standard deviation is 1 because it's a standard normal curve. And we get 0.712, which is more than half the area, as expected. There we go. Not sure what's going on here, but in any case, we finished that one up. Okay, inverse lookups with the GDC. Your calculator can find the z-score with a certain area to its left. And it only likes the left, using inverse norm, which is also a great superhero name, which is second vars and 3. So it's just below normal CDF. So suppose you want to find the z-score with an area of 0.43 to its left. Again, let's draw an area of 0.43 to its left. That'll be something over here. This must be 0.43. Must be a negative z-score to have 0.43 to its left, because we know at 0 it would have 0.5 to its left. All you need to do is type in inverse norm and 0.43. So we'll go to second vars, inverse norm. Okay. The area we're talking about is 0.43. Again, standard or mean of 0, standard deviation of 1. Gives us negative 0.176. Okay. So we just typed in inverse norm and we followed the instructions. Suppose you want to find the z-score with an area of 0.62 to its right. All right, let's draw this one. 0.62 to its right. That's going to be like over here. 0.62. It's probably going to be a negative z-score as well. It's got more than 50% to its right. Okay, what you're tempted to do is the exact same thing that we did in example 1. But remember that your calculator only likes being told about area to the left. So you have to do this little extra step. If you know area to the right, you still have to go and find area to the left. Remember, the total area under a standard normal curve is 1. So the area to the left will be 0.38. Okay, I go second vars, inverse norm. Talking about an area of 0.38 to the left. Again, standard normal curve, so mean 0, standard deviation's 1. Run it through, and I get a z-score of negative 0.305. Okay, example 3. The lengths of songs on the Billboard Top 100 chart for the past 10 years have a mean of 230 seconds with a standard deviation of 23 seconds. I have done no research on this, so I'm just making this up. 98% of the songs are shorter than some length A. Calculate the value of A. And we should also say that assume lengths are normally distributed. Our norm. So there's some length out here that we're calling A that 98% of the songs are shorter than. 98% or 0.98 of the area is out here. What we want to find is the value of this. So since we're looking for a number or a value, we're going to be using an inverse lookup. When you're looking for an area, it's going to be normal CDF. When you're looking for a score or a value, then you're going to be looking at the inverse lookup. Okay, let's see what we get. Second vars, it's an inverse norm. We want an area of 0.98 to the left. Okay, and that's good. It was set up to the left. And now we can just tell it that there's a mean of 230. And there's a standard deviation of, what was it? Of 23. Paste. It tells us that that value of A, or that length of a song, is 277 seconds. It used to be that you'd have to use z-scores for a question like this, but since the calculator really walks you through the process now of inverse lookups, we can go straight to A equals 277 seconds. Alright, the last couple of things we'll look at is binomial expansion and binomial probability. So we know that the expression 3x minus 2 to the fifth can be expanded as 5c0. 3x to the power of 5. And then the next term is going to be a 5c1. 3x to the power of 4. Negative 2 to the power of 1. Then a 5c2. I'm sorry, that should have been a 3x to the 4 outside of the brackets. Now we have 3x to the 3. Negative 2 to the power of 2. And so on. If you do a binomial expansion this way with combinations rather than Pascal's triangle, you probably are going to want to be able to evaluate one of these combinations. So 5c2, you'd see it written this way. The IB writes it as 5 over 2, kind of looks like a little vector. So you have to be aware of the context. And how we do this is 5, math, go over to PRB and go down to NCR. So 5C2. And it tells us that that's 10. Okay, binomial probability. So you recognize binomial probability from a few things. There are independent events that are repeated. multiple times. And there are only two outcomes, success or failure. Let's read through this question. Studies show that 63% of teenagers eat breakfast regularly. Suppose a random sample of 5 teenagers is taken. What is the probability that exactly 4 eat breakfast regularly? Let's see. Are these independent events? Probably. The teenagers, it's not going to matter what one teenager does to affect what another one does. Well, up for debate. Repeated multiple times. Yeah, we're going to do it for 5 teenagers. Only 2 outcomes. Either you eat breakfast or you don't eat breakfast. That lets us know that it's binomial probability. And we should check our formula book under 6.10 where it talks about binomial probability. Here's the formula that you get. Probability x equals r is NCR, p to the r, 1 minus p to the n minus r. Okay. When we interpret this, it means probability of r successes where there are n trials total and r successes, so number of trials, and number of successes, where p is the probability of success. So let's define success as eating breakfast. What we want to see in this question is exactly 4 successes. There are 5 trials, or 5 teenagers. So we're going to have 5C4, 4 successes. Probability of success is 0.63. 63% of them eat breakfast regularly. To the power of r, which is 4. 1 minus p. You might as well do this in your head. 1 minus 0.63. That'll give us 0.37 to the power of n minus r. And notice here that n and r are given to you. 5 and 4. So 5 minus 4 is a 1. And we just go to our calculator and run it through. So I go 5, math, PRB, 4. Okay. That has to be times by 0.63 to the power of 4 times 0.37. Okay, and it gives us 0.291. There's a 0.291 probability of having 4 who eat breakfast regularly. It's important to be able to work with this version of the formula or this version of binomial probability in case the variable is put somewhere kind of strange. And I've got an example of that in the stats and probability review. But in the question that we just did, it might be easier to use the normal PDF, or to use the binom PDF function. So don't use normal PDF. Not good. Okay. When you use binom PDF, it shows the probability of exactly our successes. We'll talk about binom CDF in just a second, but I want to take a look at that last question and do pretty much the same thing, but in a little more straightforward way. I'm just going to resize this. Okay, now everything fits on the page. So, studies show that 63% of teenagers eat breakfast regularly. Suppose a random sample of 5 teenagers is taken. What's the probability that exactly 4 eat breakfast regularly? We know the answer to this is 0.291. But an easier way to get there might be to use the binom PDF function. So we know this is a binomial probability question. We go second vars, go all the way down to binom PDF. And it just asks us, how many trials? There are 5. There are 5 teenagers that we're looking at. What's the probability of success? It's 0.63. How many successes do we want to see? We want to see 4. Paste. Boom. Gives you 0.291. With a little less time spent on your part. Then we could say, what's the probability that the following number eat breakfast regularly? 0, 2, and 3. We can go through the exact same process that we just went through. I want to show you one little thing, though, that you can do when you have multiple parts like this. You can go to your lists. So I press Stat, Edit. I'm going to clear out my lists. And as long as there aren't too many trials that we're looking at, this is a really nice way to approach these binomial probability questions. You can say, what's the minimum number of successes I could have? I could have 0, or 1, or 2, or 3, or 4, or 5. Next thing I'm going to do is go up into the L2 heading. So see how L2 is highlighted? Now I'm going to do my binom PDF. So I'll go second vars for the distribution. I go down to binom PDF just like I did in the last question. I'll say I've got 5 trials. The probability of success is 0.63. I'm not going to give it an X value at all. And say paste. And press enter. And what it will do is generate the probability of every possible outcome. So this one, or this one, or this one. So if I want the probability of 0 eating breakfast, it's 0.00693. If I want the probability of 2 eating breakfast, I just go over and it's 0.201. If I want the probability of 3 eating breakfast, it's 0.342. What's the probability that at most 3 eat breakfast regularly? So what we're looking for here is the probability that we have a maximum of 3, air quotes, successes. If you want the probability that x is less than or equal to 3, you could just take the probability of 0 and add the probability of 1, add the probability of 2, and add the probability of 3. And now that we've got it in lists, that's not actually so hard to do. So I have to go and find probability of 1. That was 0.05904. Probability of 2 was 0.201. The probability of 3 was 0.342. If I added all those up in my calculator, I'd get 0.609. But there's also a little slicker way to approach it. This is where binom CDF comes into play, the cumulative distribution. So let's go back up to the top of the page. It says binom CDF is the cumulative probability distribution and shows the probability of up to our successes. So if I wanted to get out of my lists and do a binom CDF on this, I can quit, go second vars. It's just below the binom PDF. There's the CDF. The number of trials is 5. The probability of success is still 0.63. And we're looking at for at most 3 eat breakfast, so the X value is 3. I can paste it in. And it figures out 0.609 for me nice and quickly. If you're not sure, stick with the binom PDF. But we have a nice little way here of doing the binom CDF and finding probability of up to 3. Alright, last one. What's the probability that at least 2 eat breakfast regularly? So we want probability that x is greater than or equal to 2. You could add up the probability of 2 plus probability of 3 plus probability of 4 plus probability of 5. Okay, that's going to work for sure. And if you have just a minute or two to spend on it, that's a great way to approach it. Probably the fastest way to do it, though, would be to realize that this is the complement of the probability of up to 1 eating breakfast regularly. And that can be had from the binom CDF. Okay, so it only does probability of up to for binom CDF. So I'd have 5 trials, 0.63. Now I want an x value of 1. Okay, so I want up to 1 success. 0.6597. $6,957. And I work that through, and I should get 0.934. It's worth mentioning that you can also use the lists for the binom CDF. So one of the things I like to do is if I have not too many trials, I'll do my L1 with the number of possible successes. Always the lowest number is going to be 0. My L2, I'll do the binom PDF, the probability of exactly that number of successes. And in my L3, I'll do the binom CDF, probability of up to 0 or 1 or 2 successes. Remember, if you want the whole distribution, you just leave the x value blank. And you need to be doing this in the list heading. See how L3 is highlighted. Okay. And not surprisingly, after you do all that, you get a 1 over here because the probability of up to 5 successes is just going to be 1. You're guaranteed to have somewhere between 0 and 5 inclusive successes. Good luck on your Math SL exams, folks. Hope it goes very well for you.